Hello everyone. I welcome you to this class of econometric methods. Myself, Dr. Muhammad Imdadul Haq, an associate professor at the Department of Economics. Today we will be discussing a special case of cointegration, more popularly known as ARDL, Autoregressive Distributed Lag Method of Regression. This is a special case. The reason being it is applicable only in certain cases. And that is that the level of integration of the variables being used are of mixed order, meaning thereby one of the variable is stationary at level and the other variable is stationary at first difference. And also there is a restricting condition that none of the variables should be stationary at second order. So, while we have discussed Johansson cointegration, we need to be clear that it is applicable. We need to be clear that Johansson cointegration is applicable only in those cases where both or all the variables are of the same order, meaning thereby they are all stationary at first difference. If you have three variables and two of them are stationary at first difference and one of them is stationary at level, then you cannot do Johansson cointegration. In that case, what we are having an alternative is this ARDL method of cointegration. So, what you have in front of you is an ARDL equation, that is yt is equal to b naught plus b1 yt minus 1, and then again more terms of lag terms of y, and then we have these lag terms of xt, that is xt minus 1, xt minus 2, and likewise extending up till say xt minus q. So this is what we refer to as an autoregressive distributed lag model. And in this, if we apply OLS, we have seen in our discussions of this lagged variable models that we are getting biased estimates in this case. And also there is a presence of autocorrelation and other issues. So the solution to it was like we had those Almonds and Coix model and Almonds model we were used as a solution to these autoregressive distributed lag models. Also these instrumental variables, they are used as a solution to this lagged models. And this was during the 1960s and 70s. Distributed lag models were extensively used, but there was a problem of multicollinearity and other things, and the solution to that was these Coix and Almonds and all this. So ARDL is used to model non-stationary time series data. In particular, we consider how they are to implement bound tests to see if the long-run relationship are present when we have a group of variables, some of which are stationary while others are not stationary. So basically it is used to model non-stationary time series data. It takes into account both unit root and cointegration. Now we do bounds test to see if there is a long run relationship are possible when variables are stationary and non-stationary both. Now there are three situations. First, all the variables are I0. If all the variables are I0, then we model time series at level and estimate the parameters simply by using OLS. If all variables are I1 and non-cointegrated, then what we can do, we can estimate this model by taking OLS after taking the first difference. Means the reason what we are doing first difference is to convert your non-stationary time series into stationary. But again, in this case, we are losing our entire losing the entire long run relationship. And the third case, if all the variables are I1 and co-integrated, then we can estimate the model by OLS using level data and estimate the error correction model. But if some variable are I0, some variable are I1, and then this ARDL method of co-integration comes into picture. It was popularized by Pisaran and Shin 1999 and Pisaran et al. In 2001. So let us have a quick look at the steps. We see that we make sure that none of the variables is I2. We formulate an unrestricted ECM, error correction model. We determine the appropriate lag. Now, this determination of appropriate lag is a very crucial issue over here, because each individual variable will have a different lag which is suitable. It was not like in the case of Johansson, you simply put it in the var and you get the lag in one time. So this process was earlier very complicated, but now with the advent of softwares, the software itself decides upon what is the most suitable lag, and we can use it accordingly. Now we ensure that all the errors are not serially correlated. We make sure that the model is dynamically stable. This is the reason. So in Johansson co-integration, we do after once we have done error correction model, means we have done the traces statistics, maxes statistics, and the error correction model, and we see ECT is fine. Then we go for a serial correlation, serial correlation test, and heteroscedasticity and normality. But in this case, there is an additional test which we refer to as Kusum squares and Kusum test. So that is required to do over here to ensure that the model is stable. Then we have to perform the bounds test to check for the long run relationship between the variables, and estimate the long run levels and restricted error correction model, and derive the long run relationship and the short run dynamics. Now, the conventional ECM, that is the error correction model in the conventional term, when we have these three variables, we can say we can have a model like this. So delta yt is equal to beta naught plus summation beta 1 delta yt minus 1 plus summation, you can say rj delta x1 t minus j plus summation sigma k delta x2 t minus k plus theta z t minus 1 plus epsilon t. Now we have to we use say any ADF test or KPSS test to check that this condition is not there. We don't have a variable which becomes stationary only after second order differencing, and then we can use this model. We can use this model here. In what we are doing, we are replacing the ECM with that is zt minus 1 with yt minus 1, xt minus 1, x2t minus 1, and this is considered as the unrestricted model. So what we have, delta yt is equal to beta naught plus sigma beta 1 I delta yt minus 1 plus sigma rj delta 1 t minus j plus sigma summation delta sigma k delta x2 t minus k plus theta 0 yt minus 1 plus theta 1 x1 t minus 1 plus theta 2 x2 t minus 1 plus epsilon t. So another pre-assumption is that the ARDL model is serially independent. Now, once we select the appropriate lag length, we can use that and we assume that there will be no correlation. Then what there is an F test can be done where theta 0 is equal to theta 1 is equal to theta 2 is equal to 0, and the alternate hypothesis that they are not equal to 0. But one practical difficulty is that the distribution of F statistics, as it is a mixture of I0 and I1 variables, is not standard. So what happened? This Pesaran and their friends, they had given bounds on the critical values for asymptotic distribution values of F statistics. They basically had give the upper bound and the lower bound to test this particular hypothesis. Lower bound is based on the assumption that all the variables are I0, and upper bound assumes that all the variables are I1. So what we have that is, if your F statistics is less than lower bound, no co-integration. If F statistics is greater than upper bound, there is co-integration. And there is a particular region where this F statistics is greater than the lower bound and less than the upper bound, then the decision is inconclusive. We cannot say whether there is a co-integration or there is no co-integration. We quickly have a look as to how it is done through eViews. So we take the data into the system, into the software, that is XYZ, and then we have our, we go to view, you go for unit root, and then you check on the level, and then we go for intercept, and we find that this, so this value is more than 0.05, it means the data is not stationary. Again, what we do, we go for estimate the equation. So for this, through this process which we have seen now, we will check for stationarity. We will see that if all of them are I1, we will go for Johansson co-integration. But if some is I1 and some is I0, then we will go for ARDL, and we will also have to check that none of them are I2. If any one of the variables is I2, then we cannot do ARDL. Then we go to quick. In quick, we go to estimate equation. In estimate equation, you will, once you click on estimate equation, you have so many models, and among this, the highlighted one over here is the ARDL model. So you select this ARDL model, and again see what regarding the lags. Nowadays, you software, you just say the software what is the auto, you just give, you just leave the option of auto, you just select the option of automatic selection, and that's it. You don't have to do anything. And again, here we have all those 4 or 5 criterias, none, and there is a constant, there is no constant, and there is constant and trend, and all those things we have over here. We select number 3 or number 4 as we have been doing in Johansson, and a result box comes out. This is not of much use to us. We move on to view, and in view you go to coefficient diagnostics, and then you go to long run form and bounds test. In long run bounds test, you will get a result output, and this is what we require. You can use this to write the equation, but the main thing over here is the bottom part. See, this gives your long run trend, long run relationship, and we see that x is also, the value of x is less than 0.05. It is significant. The probability value of z is also less than 0.05. So both the variables are significant. But first we have to check this bounds test. In bounds test, normally we do the testing at 5% level of significance. And the moment we are checking it for 5% level of significance, the lower value is 3.79 and the upper value is 4.85. My F statistics value, it should be more than 4.85. In this case, it is 7.09 is more than 4.85. Hence, we can say that there is a long run co-integrating relationship between between the variables x, y and z. Also, we have again go to view coefficient same diagnostics, and then we can find go to the error correction term. So when we select this, we get the error correction term over here, and this is 0.29 minus 0.29. So it is less than 0, one condition, or it is less than 1, and it is negative, fine. And if you see, the p value is also 0.000, meaning thereby the p value is less than 0.05. This indicates that the error correction term is significant. So all the three conditions are satisfied, and we can say that the error there is a chance of a presence of co-integrating relationship. But we have to check few other things also over here. So now we go to the stability diagnostics. We go to view and the stability diagnostics. In stability diagnostics, we are okay. In stability diagnostics, we will go for recursive estimates. We will go for recursive estimates, because here we have to ascertain that the model is stable. When we go to recursive estimates, there are two options, Kusum test and Kusum squares test. We will do each one of them one by one. So first we do this Kusum test. Upon doing Kusum test, see, this blue line, it is falling in between these two. Fine, the model is stable. Next time, we go for the second one, that the Kusum of squares test. We come over here, but see, now the blue line has crossed. So, our model is not stable. We cannot use now this model for meaningful interpretation. It is not stable over here. One of the way out is to check for a structural break and accommodate in the data. But that is again beyond discussion of this course. But we have to check for stability by using Kusum and Kusum squares. Next, we again go to check for residual diagnostics. Now you check for serial correlation. In serial correlation, you do it by that Bush-Godfrey serial correlation test. Here we check this probability of observed R square. Here the null hypothesis is no serial correlation. Null hypothesis, no serial correlation. Alternate, yes, there is serial correlation. Our p-value is less than 0.05. So null hypothesis is not accepted, meaning thereby there is a problem of serial correlation over here. Next, we can check for residual diagnostics. Again, heteroscedasticity. In heteroscedasticity, what we find, we go for Bush-Pagan-Godfrey test. That is Bush-Pagan-Godfrey test. You click on OK. Now again, your observed R square, the probability. Now this here, the null hypothesis is the errors are homoscedastic, meaning thereby there is no problem. My p-value is more than 0.05. It means there is no problem of heteroscedasticity. So two problems we had faced. One is of stability of the equation and serial correlation. Another thing which we do is the Ramsey test. This involves regressing the fitted values of the original regression on additional powers of the independent variable and testing whether these additional terms are statistically significant or not. So if they are, it suggests that there may be a specification error in the original model. Now, this is a statistical test used to detect for misspecification of the model, and if there is an omitted or a functional specification. Here the null hypothesis is there is no misspecification in the model. So in the Ramsey reset test, also it can be done from here only, stability diagnostics, Ramsey reset test. Once we go over here, now you see the model here in this case is not correctly specified, as the Ramsey reset test has the p-value of less than 0.05. That is, it indicates the rejection of the null hypothesis of no specification, no misspecification, sorry. So, meaning thereby, so if the p-value is less than 0.05, as in this case over here, it indicates that the null hypothesis, that there is a chance of misspecification in the model. So, this could be one of the reasons why our stability test is not going fine. A new addition to this has been in the form of a non-linear ARDL. We quickly have a look at it. In this non-linear ARDL, we decompose this impact of xt into plus and minus. So what we do through the application of non-linear ARDL, x is decomposed into positive and negative shocks. This is an addition to the ARDL method, and now here we have the equation. So yt is equal to b naught beta 1 yt minus 1, and see here it is a plus. So we decompose it into the positive effect change in x, what will happen on y, and if there is a negative change in x, what will happen to y. And then we have the lag terms yt minus 1 in the delta form. Then again there is a plus sign missing over here. We have xt minus 1 in the and then delta xt minus 1 and delta xt minus 1 in the plus and minus format, and then we have our third variable and our again in the b3 zt minus 1, that is the third variable over there. We quickly have a look for this. Once you have done ARDL, then you go to view and you will come over here in labels. Once we go to labels, then a dialog box will come up over here. Here you have to write asymmetric var, ASYVARS. This type of coding you have to do. It's not basically a coding, simply you have to write a command ASYVARS, and here you will write the variable x or whichever variable you want to decompose the effect of. So we have done ASYVRS and we have written x. Once we have done this, now an output box comes, not of much use for us. This is what we need. Herein again, the beauty of this model is it says that in the ARDL model, these both of them values x and z were significant, very fine. Here what it is saying, if there is a positive change in x, this is not having a significant impact on y. But if there is a negative change in x, there is a significant impact. And as in earlier case, z was significant there also, and here also z, the p-value is less than 0.05, so it is significant. So this is the beauty of non-linear ARDL, where you are incorporating the impact of a positive and a negative shock. That is why we call it non-linear ARDL. Again, this other things are the same like ARDL. You have your F statistics, you have a 5%, the upper bound is 4.35, your 6.50 is more than 4.35, so there is cointegration. Then what we can do, we can also estimate the error correction model. The error correction model is minus, it is less than 1, and also it is significant. So error correction model is fine. Then we go for the serial correlation test. We find that the null hypothesis of no serial correlation is not accepted, meaning thereby there is a problem of serial correlation. And then we have this heteroscedasticity. Here the the probability value is more than 0.05, implying that the error terms are homoscedastic. There is no problem. We can check for normality also, the Jarku-Bera. Here the null hypothesis is the residuals are normally distributed. We use by Jarku-Bera test, and your probability is 0.00. It is less than 1. So it means the null hypothesis that the error terms are normally distributed is not accepted, meaning thereby there is a problem of normality of data. Here null hypothesis, errors are normally distributed. Alternate errors are not normally distributed. Apart from that, we will again go for Kusum test. When we go for Kusum test, it is fine, no problem. But again, next we will go for Kusum squares. Kusum squares, again it is there is a problem of it. In non-linear ARDL, there is another way out, that when you go to over here, we can easily select non-linear Kusum square graph. So it will give you both the graphs. It will give you both the graphs, Kusum squares, Kusum graph and Kusum squares. Apart from that, you also need to do one more. This is called as NRDL multiplier graph. There is an additional graph over here, NRDL multiplier graph, and that is like this. Now again here, this NRDL multiplier graph is falling between the two extremes, so that's fine. NRDL graph is fine over here. So by using this, and all this you get from this window in the add-ins, like I just show you in the add-ins. You have to go to add-ins, and there you will find make nonlinear ARDL. All these things will come one by one, and then you again go to view and you can select the error correction. You will find the error correction term and the bounds test and all the things which we have done and shown over there. And the beauty of this NRDL is it incorporates nonlinear relationship also into the model. So I hope the discussion on ARDL is clear to you. The only thing we need to keep in mind, we use this if some of the variables are I0 or some of the variables are I1, and provided that none of the variables is I2. With this, we conclude this session. Thank you.